This is question 316. Consider a film of liquid draining a volume flow rate Q down outside of a vertical rod of radius A, as shown in figure P13 here. P16, some distance down the road, a fully developed region is reached where fluid shear balance gravity and the thin film thickness remain constant. Assuming incompressible laminar flow and negligible shear interaction with the atmosphere, find an expression for Vz R as a relation between Q and film radius. So here is actually we need to calculate the velocity downward like this one. But if you use Navier-Stokes equation, so it is you must be very particular because this is the axis of Z. So we have the axis of R here, and we have the axis of theta as the tangential velocity. So in real situation, we found that the flow will flow down from top to bottom like this one. So means that we are calculating the velocity of Vz. So I hope you could understand this idea. This is something like, for example, if you have a beaker here. So for example, you have a beaker and then you pour a liquid or on a road like this one. So if you pour it very carefully, so the fluid will flow smoothly on the road like this one. So we imagine that from the top view here, so we have a road and then the lubricant is the liquid will flow around the road like this one freely, okay, equally with equal film thickness. Okay, so it means that it's flow with gravitational force. So and then if we draw the velocity distribution, so we have might be something like this one. Okay, because we assume that there are no slip condition at this surface. So what we do is we write down the Navier-Stokes equation for z-axis, and then the common mistake for student here is actually if we solve Navier-Stokes equation for Cartesian coordinate, we can only remember the x equation, then we could apply for y and z because the equation is totally the same, only the terms is different. But for Navier-Stokes equation for polar coordinates, please make sure that you remember all the three axis Navier-Stokes equation. But don't worry, in final exam or in test, I will give you the notes for the Navier-Stokes equation. So I already gave you in your WhatsApp group, in our WhatsApp group, a PDF listing all the Navier-Stokes equation. Okay, so means because the Navier-Stokes equation is different from r axis, theta axis, and also the x axis. So at this moment, for example, we take the x axis here, and then we could do our calculation. So simply you could do this at home. Normally at this one, because the flow is fully developed, the flow is steady flow, so we could have the value of 0 at the left hand side. So and then for the right hand side, so for sure the gravity cannot be neglected, and this time the gravity is work vertical like this one, so means that we don't have to split it into its component. So and then because when this situation it is open to atmospheric, so means that the pressure here is PATM, so we assume in gauge pressure. So I think you already know we in measuring pressure, we have absolute pressure and we have gauge pressure. So if gauge pressure, we assume that PATM is equal to 0. So if we measuring or calculating as an absolute pressure, so you need to take PATM is equal to 101.3 kilopascal, at least the common value. So because it is open to atmospheric, So we assume that the pressure is equal to 0. So and then here again, I hope you could understand, you could imagine what is the meaning of the symbol here. So it is not just a derivation. Sometimes you need to reflect the derivation there in physical meaning of them. So for example, the idea of du dz here. So du dz means, so we have a road here. So and then we have a value. So and then du dz mean if we have a streamline here, so we have 2 points, so mean the value of uz here and uz here is not changes because it already flow in steady. So means that it cannot change by time. It's always same at all the point. So means that there are no du dz. So and then the du d theta. So if we look from the top here, so if we take one radius, so the amount of uz here and here will be the same. So means that there are no du dz actually. So the remains term here is actually the du dr. So du dr means that if we look from the top here, so we have an r radius, so the value here and the value here must be different because we have a velocity distribution like this one. So mean there are changes of velocity along the r axis. So this is actually the very fundamental that you need to understand, because you cannot remember all the condition from tutorial question like this one. You need to understand the situation and then you need to suit with your condition, your experiment or your situation. So but actually this is the basic idea to know about that. So and then we bring the value of the rho g here. Okay, the terms here, we bring the rho g, the gravity is here. So and then we get the -1. So and then here is actually what I give you in the notes. Okay, sometimes we are stuck because we have difficulties to integrate because one of the term have double differential form here, and then we have just only one differential terms here. So and then actually it is come from this term. So I hope you could look back with the PDF notes or my previous lecture video. So I show you about this one. So and then because in certain textbook they use this idea. So because this idea is quite simple to do the integration later on. So we bring the r, and then it seems that we need to integrate 2 times. So we integrate 1, we bring the dr here to the right hand side. So we integrate 1. So and then we could get this one, and it's come with the constant c1. And then we integrate for the second time, so we will get the value of u is like this one. So here it remains two constant c1 c2 to be determined. So here we put the boundary condition as this one. So we assume that the r is equal to a, so the velocity is 0. And when r is equal to b, so we assume that mu du dr is equal to 0. So I think you already know the meaning of this one. So after that, we substitute into the equation. We could get the C1 is equal of this, and the C2 is equal to this. And then if we substitute the value of C1 and C2, then we factorize certain item. So we could get the U is equal of this one. So and then to calculate the flow rate. So the idea is simple. We are still using the Q is equal to A and V. So and then A and V here is actually, V is the velocity. So for sure student will take this one. But the A here is the cross-sectional area. So the cross-sectional area, so the hint is it must be perpendicular to the flow. So if we have this one, so and then we have a fluid on this side. So actually we need to calculate the cross-sectional area as this one. So because this is just an O-ring or something like an O-ring from the circular area. So we need to calculate as, okay, we assume this is dA. So normally the simple idea is the area of A is pi r square, and then we have dA is equal to pi r dr. Okay, so and then that's why we put 2 pi r dr in the integral form, because it reflects the idea of this one. So again, and then we substitute the value of Vz, we substitute the value of A here, and then we do the integration. However, when you do the final, okay, so when you do the final calculation, you must be careful, because the limits here is actually cannot start with 0, because if you start with 0, for example, we have a road here. Okay, this is the axis of r. If you start from 0, means that you are calculating from here to the outer one. So you need to start to calculate from the here. So mean this is the A, and this is the maximum radius B. So we put A is the minimum radius here, and B is the maximum radius. As I said, I hope you could understand what you do, so it will reflect the situation that you have. Okay, in certain idea, maybe if we only talking about the fluid flow down in circular shape like that, maybe you could integrate from 0 to b to the maximum radius. But in this situation, you need very careful with the limits. So and then if you do this, so you have this term of flow rate.